Okay, page 9 of Math Induction, problem 11. Prove that this term, u subscript n, equals 2 to the nth minus a negative 1 to the nth power divided by 3 is an odd number for all positive integers n. Okay, so first we want to write that the proposition subscript n is this. I'm going to write that down. And then the first n value is 1, so if n equals 1, what do we know? We know that this is odd. So we could write u subscript 1 equals 2 to the n, not 2 to the n, 2 to the first, minus negative 1 to the first, divided by 3 is equal to 2a plus 1, where a is an integer. But instead of saying that, let's just say, oh, it's odd, because we're going to be able to calculate the value. So let's see if that's true. u1 equals 2 minus negative 1 to the first is negative 1. So it's 2 minus negative 1 divided by 3, which is equal to 2 minus negative 1 is 2 plus 1, which is 3 divided by 3, which is equal to 1, and 1 is odd. So it's true. Okay, therefore, p subscript 1 is true. If p of k is true, then blah, blah, blah. So we're going to assume now that p of k is true. P of k would be u subscript k equals 2 to the k minus negative 1 to the k divided by 3, and that is equal to an odd number. So we could say that by saying 2a plus 1, where a is an integer. So we're going to assume that that's true. Now let's do the k plus 1th case. So the k plus 1th case would be, we're going to start with this left side and see if we can get it to here. So we're going to say uk plus 1. We know the left side is the definition of u of k. So we could put 2k plus 1 minus negative 1 to the k plus 1 divided by 3. And now what we're going to try to do is we're going to try to make this look like this, okay, and then try to substitute in something like this. So let's see, what if we, instead of 2 to the k plus 1, what if we wrote 2 to the k times 2 to the first? Instead of negative 1 to the k plus 1, what if we put negative 1 to the k times negative 1? And then it's all divided by 3. We didn't quite get it to the point where it looks like what's boxed in orange. So let's try to meet us halfway. So we're going to take the part that's boxed in orange, which is this, and then and that's equal to 2a plus 1. Let's modify that so that we just get maybe 2 to the k by itself. How do we do that? So we'll say 2 to the k minus negative 1 to the k is equal to 6a plus 3. Okay, and then let's get 2 to the k by itself. So 2 to the k equals 6a plus 3 minus or plus negative 1 to the k. Okay, now let's put that in for here. Let's do that. So now we'll have 2 times 6a plus 3 to the that's messy, minus plus negative 1 to the k plus negative 1 to the k divided by 3. Is that good? Okay. Remember that we're trying to get something that looks like this on the right side, okay? So let's distribute the 2. then we'll get 12a plus 6 plus 2 times negative 1 to the k plus negative 1 to the k divided by 3. Now this is equal to 12a plus 6 plus 3 to the negative 1 to the k, because I got like terms there, divided by 3. Now I can rewrite this as 12a divided by 3 is 4a. 6 divided by 3 is 2. 3 divided by 3 is 1. So now I got 4a plus 2 plus negative 1 to the k as my right side. Now, is this an odd number? So this is definitely an even number, right? Because 4a, where a is an integer, is going to be a multiple of 4, which is definitely an even number. 2 is going to be an even number, okay? And then look at this. So this is going to be either negative 1 or 1, depending on the value of k. So if I have an even number minus 1 or an even number plus 1, then it's always going to be odd, right? So I think we've done it. So we can just write down here that u of k plus 1 is equal to, we can write down 2k plus 1 minus negative 1 k plus 1 divided by 3 is always equal to an odd number, so 2b plus 1, where b is an integer. If u of k is assumed to be an odd number where a is integer, okay? And then finally, since p of 1 is true, and p of k plus 1 is true whenever p of k is true, then p of n is true for n is a positive integer, okay? All right, moving down to number 1 of 9b.3. Use the principle of math induction to prove the following propositions. Okay, so this proposition is, by the way, did I? Yeah, I did. So for this one, the proposition p subscript n is this, okay? Yeah, they give us a hint here. Okay, so it's for positive integers n, so the first value is n equals 1. What does that look like? So if n equals 1, then the left side is going to be 1 minus 1 over 2. That's the first term here. So it's just going to be one term. It's going to be 1 minus half. So that's the left-hand side. And then the right-hand side is going to be this, 1 over 1 plus 1, which is 1 half. So yeah, it works. Okay, so as a result, we can say that p subscript 1 is true. Okay? All right. If p of k is true, then we're going to assume that this expression with k in it is going to be true. So we're going to put 1 minus 1 half, 1 minus 1 third. Oops. 1 minus 1 fourth. Dot, dot, dot. Multiplied, the last term is going to be 1 minus 1 over k plus 1, because we're putting k's in for n, equals to 1 over k plus 1. Okay. All right. Now we are going to write the k plus 1 statement. So we're going to start with this left side, and we're going to just make it go up to k plus 1 instead. So it's going to be 1 minus 1 half, 1 minus 1 third, dot, dot, dot. and it'll go up to 1 minus 1 over, so it's k plus 1 plus 1, so it'd be k plus 1. Oh, so let's write it, the kth term and the k plus 1th term, which should be that one, okay? And then we're going to try to make it look like that by substituting in. So do you see how this is equal to this? So let's substitute that in. So we got the orange part is going to be 1 over k plus 1, which we assume to be true. And then we multiply that times 1 minus 1 over k plus 2. And let's see what that is equal to. So let's try to maybe, what we want to do is we want to make it look like this. 1 over k plus 2, because if you put k plus 1 in for k, then you get 1 over k plus 2. So in this case, let's see, we got, I don't know what I should do first. Let's just distribute the 1 over k plus 1. So we get 1 over k plus 1 minus 1 over k plus 1 k plus 2. And now we make a common denominator of k plus 1 k plus 2. So it's going to be k plus 2 divided by k plus 1 k plus 2 minus 1 over same common denominator. So the top is going to be k plus 2 minus 1, which is going to be k plus 1 on top. And on the bottom, it's going to be k plus 1 times k plus 2, and cancels out. And we end up with 1 over k plus 2, which is what we were trying to get, right? So we did it. All right. So here we're going to say 1 minus 1/2, 1 minus 1/3, dot, 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 1 minus 1 over k plus 2 is equal to 1 over k plus 2. If 1 minus 1/2, 1 minus 1/3, dot, 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 1 minus 1 over k plus 1 is equal to 1 over k plus 1. Okay, since p of 1 is true and p of k plus 1 is true whenever p of k is true, then p of n is true for n is all positive integers. Okay, and that is it for page 9.